Hey everyone. I hope that you guys are having a good start to your week. I hope if you watched the Super Bowl, you enjoyed that. If you didn't watch the Super Bowl, I hope that you did something that you enjoyed, and I hope that you overall had a good weekend. Um, I am ready to talk about proteins. Um, I've got some poll questions that I'm going to go ahead and kick things off with. I will share those in just a moment. Polls, there we go. These are our opener questions for today, the 9th, February 9th, 2026. While that's opening, while y'all are looking at that, I'm going to go ahead and open the files that I want to open. Also going to stand up. I'm not that tall. My ceiling is just short here. Okay, so we have talked all about classification of amino acids. We have talked about amino acid structures. We've classified our amino acids based on their polarity, going with the major groups of polar positive, polar negative, polar uncharged, and non-polar. We've also elaborated on how there are other ways in which you can classify amino acids. Specifically, they can be classified as aromatic. Those would kind of fall into that polar, non-polar area. But also they can be classified kind of nutritionally from the standpoint of are they essential or non-essential amino acids? Now, along those lines, we also discussed the single letter and three letter codes of our proteinogenic amino acids and how different amino acids will undergo changes based on different environmental conditions. Now, one of the things that we discussed at the tail end of last class was we talked about how different amino acids or different proteinogenic amino acids they can have different charges depending on the conditions they're in. And I'm going to use the proteinogenic amino acid arginine. Arginine is represented by the single letter code R and the three letter code ARG. Now, ARG is your three letter code for this. This is an amino acid that has three ionizable groups. Every amino acid has two ionizable groups. Every proteinogenic amino acid has at least two, but arginine has a side chain that's ionizable. Now, one of the things that I mentioned with respect to your amino acid structures and my expectation for y'all is that I want you to be able to identify them, draw them as it comes up during our discussion activities, and I want you to also be able to look at an amino acid and make a kind of educated guess about its pKa values. I don't want you to commit specific pKa values to memory, but one thing that I do want you guys to know and think about is to think about the N termini. So I'm going to write N. I'm going to use a lowercase n here and then a lowercase c here to distinguish between single letter codes there. So my N here, I'm going to put the pKa value of this at approximately, let's go with 9.1. Now I've arbitrarily picked something, but not arbitrarily picked something where, it's anywhere between here and 1 million. I just got a private message that says I was marked absent on these dates, even though I attended and participated in both Zoom classes. Could you fix my attendance when you get a chance? Thank you. I don't think that, sorry. I just was a little bit late. I will check again, but I don't think that I've actually updated the um, attendance for those days. If there is a zero there, that means I did do that. I did update that. Um, in which case, yes, I'm going to go back and look at these. But if there is a blank there, that means no grade has been entered. So the grade book is very particular. If there's a number there, it can use that to calculate an average. But if there's a blank, that just means nothing has been entered. I'm a little bit behind on those, and I apologize for that. Okay, so back to the N termini here. So I'm talking about the left-hand side of my amino acid, the N termini of arginine. I put the pKa there at about 9.1. Why did I pick 9? Well, the reason is because the N-terminal group of most of your proteinogenic amino acids is approximately 9. 9.1, you could have put 9.3, whatever. That is a number that I will give you those values. Now, I'm going to go to the other side, the C termini. The C termini is going to have a pKa value that's approximately, I'm going to give it about a 2.1. Now, that group will have a pKa closer to 2, so that's why I landed at 2.1, just something close to that. Now, the R group for arginine, I always get arginine and lysine mixed up, but if I remember correctly, arginine is about 12.4. So for our purposes right now, though, I'm just going to go ahead and proceed with that as the specific value. Now, we would classify arginine as a PP or a polar positive amino acid. So that means that and what we're trying to do here is look at all the possible charges that this molecule can have and then calculate the PI, because that was what we were kind of wrapping things up with at the end of our last class. So if this molecule is in a solution with a pH of 1, that means this group where I've drawn a circle, this group where I've drawn another circle, and this group are all protonated. Now, the N termini, when it's protonated, it's positively charged. The R group, now this is arginine's R group, so it's kind of a double R there. That is also going to be positively charged when it is protonated. The C termini is going to have a charge of 0 when it's protonated. So what that means is that arginine is an amino acid that can have a charge of +2. This amino acid is, barring some sort of modification, it's unlikely to have a pH, or it's unlikely to have a charge of +3 or anything more extreme than that. Now, when we deprotonate these groups, so if we add a strong base, then we're going to begin deprotonating groups. Now, I've left the quiz or the opener questions up for about 8 minutes. I'm going to go ahead and end the poll right now. So thank you for participating in those. We're going to revisit those topics as we move through today's class. So this molecule will have a charge of +2. Could everyone give me a 1 in the chat if they're good with arginine being a +2 at a pH of 1? Any other character will be your way of indicating, hey, I'm mixed up on this. Okay, so I'm seeing lots of I'm seeing lots of 1s, so I'm going to go ahead and proceed from here. So, like I said, the N termini and the R group are both positively charged whenever they're protonated. The C termini has no charge whatsoever, so it's neutral. That happens to be the first group, I'm going to draw an arrow to it, that we're going to deprotonate.
Yes, ma'am, I am. I just answered a question. Yes,
Jackson, do you have a question for me, or is it accident?
no, I'm sorry about that.
No worries, I'll mute you. Okay. Usually whenever that happens, students just kind of like mute themselves and disappear. Thank you for not disappearing and just saying, oh, no worries. Okay, so our first group, when that gets deprotonated, our molecule will go from a +2 to a +1. Now, the next group that we're going to deprotonate happens to be the N termini. When we deprotonate that, which is going to occur when our solution's pH has gone above 9.1, that means our molecule is going to have an overall 0 charge. So what that means is that the C termini will be negative because that goes from neutral to negative. The N termini will transition from positive to zero, and we're left with a positively charged R group. So essentially, the C termini and the R group, those two charges will offset one another. Now, eventually, whenever we raise our pH up even more to above 12.4, where that group, that R group of arginine, has a charge of zero, we'll get to a point where our molecule has an overall charge of -1. So we had three groups that are ionizable. We deprotonated each one of them, and we went from, well, having a charge of +2 to when those three groups are deprotonated to having a charge of -1. Arginine, as a polar positive amino acid, can be +2, +1, 0, -1. Anything outside of that, it's virtually impossible for arginine to do. However, with some sort of modification or something like that, it could happen. But generally, when we're talking about the proteinogenic amino acid arginine, this is our limitation. Now, with that in mind, the way that, so this is, we've drawn out all of our pKa value, or we've drawn out all of our possible charges. The next step is to say above those arrows, write our pKa values: 2.1, 9.1, 12.4. If we wanted to figure out the pi, so where 100% of our molecule has a zero charge, we would take 9.1 as one pKa value. What other pKa value? Add it to the chat, please. 12.4. So we're going to take 9.1 and 12.4. We're going to add those two together and divide by 2. And whenever we do that, we'll get 21.5 divided by 2 is about, what, 10.7, roughly? 15.21. 9.1 plus 12.4. So 9.1 plus 12.4 is 12.5 plus 13, or plus 9 is 21. 10.75. Thank you. Can anyone confirm 10.75 with me and Bianca? Thank you. All right, wonderful. So that's how we calculate our PI. We didn't have to draw the molecule at all. What did we have to do in order to work through this? Okay. All that we had to do was we had to, or what helped us along this way was to classify this amino acid as a polar positive. Then we worked through and said, okay, well, when this is extremely acidic, here's the charge. When it's extremely basic, here's the charge. We list all those out. We find a place for each one of our pKa values. We add a pair of pKa values. We divide them by 2, and we get our PI. Now, will this look a little bit different for a polar negative amino acid? It will. Why? Well, we'll use different pKa values. In addition to that, a polar negative amino acid isn't going to have such an extremely positive charge. Okay, so I hope that everyone's feeling all right about that. That is an important skill and an important tool to have. What we're working on today, however, is we're building from there. Do we always use the N termini and the R group? Okay, that's a great question. No. And it's going to be influenced by or dictated by, well, how do you classify that how do you classify that amino acid? Just a little bit of a preview, if you were to do a polar negative amino acid, in that case, chances are you're going to be using the the C termini in the R group. It's important to basically work through this same pattern of identifying all the possible charges and then identifying the pKs that correspond to those. Okay. So we'll proceed from here to talk about our different levels of protein structure. Now, protein structure is something that you're probably a little bit familiar with. And if you're not, that's okay. It's just a matter of taking what makes it or the building blocks for a protein, your amino acids, your proteinogenic amino acids that we've already talked about, and thinking about how do those fit into something considerably larger. So we have a total of 4 levels of protein structure. I really like biology and biochemistry because this is the time whenever I'm like, somebody didn't really take a lot of lessons from a creative writing classes or class. That's my bad joke, but our levels of structure are primary, secondary, tertiary, quaternary. There's a part of me that's just like we didn't want to name it something more fun, but that's that. Okay, so our first level of protein structure is the primary level. Now, what does the primary level consist of? It consists of the amino acid sequence in the N termini to C termini direction. Notice how whenever I show you an amino acid or kind of reference an amino acid, the N termini is listed on the left, the C termini to the right. There are already so many things. And I respect, I understand. That makes sense. You're right. It's good to appreciate that. So we've got the N termini going to the C termini. Now, our secondary structure is kind of your local structures. There are 2 major examples of your local structures known as the alpha helix and a beta sheet. Now, I'm going to move through these a little bit quickly because we're going to revisit all of them in due time. The tertiary or third level of structure is R group interactions, and the fourth level is your subunit interactions. Now, these last two, your tertiary and quaternary structure, these are basically what does a protein look like in 3D. Now, the way that I always kind of think about the different levels is there's more organization that's being put on these different levels, and there's more information that you're getting with these different levels. Your primary structure, your primary structure is going to look something like this. R, A, D, G, B, not G, R. Yeah, there we are. RADGR. Okay. This would be the sequence of amino acids listed first from your N termini to the C termini. And now this could go on for quite some time longer than that and for more amino acids, but that would be a visualization or a depiction of your primary structure. Now, getting this single letter coding, we have none other than Margaret Oakley Dayhoff to recognize and thank for that. Now, when it comes to the structure, the primary structure, it feels a little bit like structure's I don't know, almost like misrepresentative because it's like, well, it's not. That's like saying, "Hey, watch me draw the letter R." Done. I drew it. There you go. It's I wrote it. And if I want to say I drew it, then that's fine. I don't know that anyone's going to really argue at this point, but there's not a lot of complexity to that. Now, when it comes to the primary structure, the first thing that you need to know is that we read it from the N termini to C termini. Now, it is stabilized by covalent bonds. Now, this right here, I'm going to circle the peptide bond or all of the atoms that make up a peptide bond. But before we do, or as we're looking at that, and we've got this green bond that's highlighted, could anyone tell me the functional group that constitutes the C termini of an amino acid? Yeah, carboxyl group. So we've got a C O O H. If it's acidic, but chances are at a neutral pH, it's going to be COO minus. Okay. Now, the N termini of an adjacent amino acid is going to look something like this. Okay, so there's my N termini. That's at a neutral pH. When these two groups, this one on the left, and this one on the right react together. They will form this green peptide bond. Could anyone tell me basically what are the atoms that are missing from these two functional groups when they form that peptide bond and what those atoms are, what they make? Michael, I'm not sure if you were saying OHH or if you were going, oh, either way, I think spot on. That's absolutely right. We have an oxygen over here, and we have a pair of hydrogens that basically go missing because in the formation of this peptide bond, what do we produce? None other than water. Now, how's everyone feel about that? Give me a 3 if you're like, oh, okay, I can see that. And any other character if you're like, what? Okay. So we've got our C termini, and then we've got our N termini. Now I want you to look at the C termini, which has our right here, and then our N termini. Could anyone tell me, looking at the with the arrows that I drew, Y or N, are those two groups that I have arrows pointing to, are they charged? Yeah, absolutely. The carboxy termini, the C termini is going to be negatively charged at a neutral pH, and the N termini is going to be positively charged. Now, could you tell me and spend a minute, look at the peptide bond, and kind of, be critical. Do you see a full-on charge on that peptide bond or near that peptide bond? And those charges are denoted with a plus or a minus. Tell me Y or N, do you see a charge on that peptide bond? You're getting lots of no's. You're absolutely correct. So if we are thinking about a single amino acid, or let's say that we've got 5 different amino acids that we're looking at individually, for all of those individual amino acids, we're going to account for the R group, the N termini, and the C termini when we're trying to figure out what's the overall charge of that. When we have a reaction that leads to the formation of a peptide bond, these two groups, this C termini and this N termini, that were charged when they were part of individuals or when they were parts of the monomers, they are no longer charged things that we need to account for. So if you think back to those questions that I had as our starters, a peptide bond isn't going to have a charge or isn't going to have a formal charge at a pH of 2. It's not going to have a formal charge at a pH of 11. It's not going to basically be charged at any point across the spectrum of pHs. That's an important thing to remember because if we think about, let's go with glutamic acid. I'm just going to pick out glutamic acid. I've drawn an arrow pointing to this glutamic acid as a part of this polypeptide or a part of this protein. If you had a free-floating single glutamic acid amino acid, how many pKa values do you need to account for? Glutamic acid, also known as glutamate, it's a polar negative. So you're absolutely right. You got 3 pKa values you've got to account for. Okay. Now I want to bring you back to here. I'm going to draw a smiley face. For this glutamic acid is a part of a polymer. How many pKa values do we need to account for this glutamic acid whenever it's a part of this polymer? Well, for that individual glutamic acid, well, 1. Now, I think that based on the responses that folks were giving, if we're talking about determining the overall charge for this whole molecule, then we have to look at every single amino acid's R group pKa value. Does that make sense? Now, when we're looking at this whole thing, which my stylus is being a little bit delayed now, when you look at the pK or when you're trying to figure out the charge of an entire protein, yeah, you've got to go through every single amino acid's R group. Is it an ionizable group? What's its pKa? You do it that way. Glutamic acid here that I have the arrow pointing to, you do have to account for that. But that glutamic acid, when it's a part of a polymer, you are only concerned with one pKa value. Could you give me a 5 in the chat of, oh, okay, I see how that works. Okay. Now, the thing that I want you to take away from this, maybe more than anything else, is a peptide bond is not going to have a formal charge. The second thing that I want you to take away from this is whenever I'm analyzing a protein and trying to calculate an overall charge for a protein, I don't have to look at every single amino acid or all 2 or 3 amino acids of every single pKa value. Instead, I just say, okay, well, I really only need to know about the R group pKa values. So those are the important takeaways from this. Now, a primary structure is the amino acid sequence. I've used these two terms, polypeptide and peptide. I will give you kind of a definition that a peptide is typically anything less than 50 amino acids. A protein is anything more than that. Now, I will use the terms polypeptide and protein kind of interchangeably. But at this point in my life, um, no one has threatened violence on that one. And so that's kind of my standard for am I going to quibble over this? Likewise, I'm not going to ask you the question, at what point is this, or this? So I will not, yeah. But in general, 50, 50 amino acids is kind of the break point. And I mentioned that because has anyone give me a Y or N in the chat? And I don't want you to feel like you're like self-identifying as yes, this is completely relevant to me. But has anyone recently heard about kind of the rise in popularity of peptides that are, I don't know, injectable peptides that are like in fitness and fitness industry sort of things? Yes, that's my job. Oh, interesting. Well, I don't know too much about them, but one thing that I do know is I was looking, there's lots I see online of where you can get them and everything like that. Um, I don't know anything about the safety or lack thereof. Not a physician. Important thing to remember. Um, oh, very cool, Lou. That's awesome. One thing that there was one that I looked up. I can't remember what it was. They all have, these short names like um, ALM 174 or something like that. I remember looking one of them up and saw that it was like 89 amino acids. And I was like, ha, not a peptide. Um, yeah, I think that there's lots of very limited approval for them. Which ones are most legit? That's a fantastic question. I've seen some on Reddit where people show like a picture of a vial that's got like this chalky substance, and they'll basically just be asking the community, "Is this one safe?" And I think to myself, "Oh my gosh, oh my gosh!" But at any rate, um, I just, yeah, lots of. I would imagine lots of people would be like, "Yeah, it's totally safe, man." And they're coming from the standpoint of, I don't know, I used to like snort Smarties when I was in third grade, so I think it's pretty good. Okay. Kids used to get in trouble for that when I was in school. They'd get in school suspension or ISS. Okay. So Sorry, let's take a step back. Primary structure. The things that I want you to take away from this are it's just N termini to C termini. The single letter and three letter codes, they benefit tremendously from the primary structure benefits tremendously from the single letter and three letter codes. Could you list a protein using every single amino acid's full name? Yeah, you could. It's going to be a very long name for a polypeptide or a protein. Um, and so, okay, I got to turn annotate off. Okay, there we go. Um, so those are, things to account for when it comes to primary structure. N to C termini, a peptide bond does not have a charge. It is one letter and three letter codes are going to drive them. I will always identify in questions something like, here's the primary structure. If the question is to calculate the PI, I'll post that in there. If the question is to determine what is the overall charge, I'll say that. And I'll say, here is the primary structure, or here is the primary structure using the single letter codes. And one thing that's important to remember is if you see something like this, if you ever see ARK and they're all capitalized, I want you to know that you can operate under the idea that that is a peptide made up of three amino acids as opposed to the um, single amino acid, because your three-letter code is a capital letter followed by two lowercase letters. So worthwhile to remember that. Okay, now the next level of protein structure is a secondary structure. The secondary structure often refers to what are known as, or what are, sorry, the secondary structure often references local structures. These are stabilized by hydrogen bonding. This is different from our primary structure, which is stabilized simply by the peptide bond. So when you think about a primary structure, you might look at a polypeptide and say, oh, okay, well, it's an alanine followed by an arginine, followed by a lysine, followed by a glycine. But that kind of doesn't matter. That whole thing is stabilized not by what those amino acids are, but instead that there is a peptide bond that connects each one of those proteinogenic amino acids. Your secondary structure, these are referred to as your local structures. And I always kind of think about this as your primary structure is like the people who live on your street. The secondary structure is like how your street fits into a neighborhood. Okay. On this street, here's the nine people who live on it. And then the adjacent street, we've got there's we live in duplexes on this street, and then on the street next door, that's triplexes. And then the street next door after that, that would be single family homes. Not really trying to get into a zoning discussion or anything like that, because I'd be way out of my depth. But that's one way that you could kind of visualize this. How do these different components of the same thing fit together? Now, the secondary structure is going to be stabilized by hydrogen bonding. It's not just any random hydrogen bonding, it is instead the amide hydrogen and carbonyl oxygen of the polypeptide backbone that they will hydrogen bond with one another to stabilize it. If you look on the left-hand side of this figure, we've got this model right here. Our dashed lines, as is kind of always the case, represents our hydrogen bond. So there's a hydrogen bond, hydrogen bond, hydrogen bond. So these are all hydrogen bonds that help stabilize this, in this case, is a helix. Now, your secondary structure, this model shown on the left is an example of what's known as an alpha helix. An alpha helix, well, that's more than just a primary structure, which is a linear graph, or sorry, a linear model. This is showing what this thing looks like and how they interact with, how different elements of it interact with one another. Now, there are patterns, and with respect to how different amino acids in a polypeptide can fold together, and therefore your secondary structure it actually can be predicted based on the pattern or sequence of amino acids. You can put a reasonable estimation or prediction together about, oh, does an alpha helix form here? Or is there a beta sheet here? Or is this, there's no secondary structure and you just got a bunch of like random coiling taking place. Now, the amino acid side chains, also known as your R groups, can influence a structure if it's formed, but they're not seen as contributors to secondary structure. Think about this as they will disrupt or invalidate a secondary structure. It's almost like if there's a certain amino acid right here, where I, yeah, right there, that can disrupt the formation of this alpha helix, but it's not going to drive the formation of it. So there we go. Now, here what we have is a polypeptide. And one thing that I think is very important to be able to do is to look at a protein or a part of a protein like this and then pick out different elements of that structure. Because I think that it's very easy to kind of fall into the trap of just being like, oh yeah, cool, there's a peptide, got it. You have kind of an expectation. Every proteinogenic amino acid has the following backbone: N, C, C, followed by N, C, C. So I think that a good idea, or I think it's a good idea to figure out those things that you know and mark them. Say, here's my N termini. And I've switched to a highlighter, so I hope that you can see that. Then I've got C, C, N, 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 C, C. Now, if it was a little bit confusing for the sequence and the cadence that I was using, I apologize for that. Um, but I think that after you've done that, it makes it a little bit easier for you to pick out. And here we do have the advantage of the peptide bonds are pointing out. Hey, my audio stopped coming through. I'm going to try switch back devices. Okay, sounds good. Um, we've got the peptide bond highlighted here, but I always like to just draw an arrow or draw a line to say this is my peptide bond. And that peptide bond is going to be a carbonyl carbon going to the N termini. So the C termini of one amino acid to the N termini of my next amino acid. So there we go. There we go. There we go. Now, after we've done that, I'm going to switch colors for this because what I want to do is I want to highlight the atoms that make up my R group. So here, the first alpha carbon, which is right there, and I'm going to go ahead and highlight or point with a green arrow my other alpha carbons. And I know that these are my alpha carbons because I've got my peptide bond. And then after that nitrogen, I've got my alpha carbon. Peptide bond, nitrogen, alpha carbon. Peptide bond, nitrogen, alpha carbon. Peptide, nitrogen, alpha carbon. I think that it's really helpful to, you know, some people I think are capable of doing this and being like, ah, slam dunk, but I personally struggled with this. So as soon as I find my alpha carbons, then I can say, well, I know on my alpha carbon I've got a hydrogen, and then some whatever is not the hydrogen is going to be my R group. Now this first one on the N terminal, my N termini, my N terminal amino acid is a glycine because I've got a hydrogen and lo and behold, another hydrogen. When I have two hydrogens, I know that the amino acid there is glycine. My next alpha carbon, which I'm going to draw alpha 2, I've got a hydrogen, but then I've got, oh, nice, my CH2 and then my ring. Okay, so that would be my phenylalanine. Now on to alpha carbon number 3. We've got a hydrogen and then a, ooh, carboxylic acid. A carboxylic acid with only one CH2, therefore this is aspartic acid. Then we've got a threonine. We've got that hydrogen, and then my threonine. My alpha carbon shows my next alpha carbon. Sorry, 3 alpha 4. My fifth alpha carbon has a hydrogen and a methyl group. That is alanine. Then my sixth alpha carbon is going to be a hydrogen and this group that looks a lot like aspartic acid, but it's aminated, therefore it is asparagine. Okay, now the last group, or the last functional group, my C termini, one thing that I want you to recognize about this is that it is deprotonated. So it's negatively charged. Now, when you look at this molecule's overall structure, which I apologize, I've got lots of markings on it, but I was playing with that. Lots of markings there. One of the things that I want you to be able to do also is say, well, what's the overall charge of this molecule? Well, the overall charge of this is we've got a positive on the N termini, a negative on the C termini. So the overall charge of this molecule adds up to be, that's right, you guessed it, 0. Because none of the other groups have any sort, they may be protonated, but none of the other groups have an overall charge. Now, if we wanted to say, calculate what is the extreme end charge of this molecule, like how positive could this be? Well, we'd look at each of our amino acids, which we've got glycine, phenylalanine, aspartate, threonine, alanine, asparagine. Lou's voting for +2. I got to be honest. I'm going to vote for my C termini when that's protonated. That means this group is 0. But unless I'm glycine can't be protonated, phenylalanine the same, aspartic acid is already protonated, has a charge of 0, threonine 0, alanine 0, asparagine is a polar uncharged amino acid. So this overall molecule, I'm looking at it having a charge of +1. Can you give me a emoji in the chat if, yeah, I see that, or a letter in the chat if I'm not seeing it? And then if you're not seeing it, if you could tell me where. So what we're trying to do is figure out what's the overall possible charge where if every group is protonated, then what is the charge? So we look at all of the ionizable groups. And where we want to start is on the termini. So the N termini here is already protonated. That can't get any more protonated. The C termini is deprotonated. If that group were protonated, it would have a charge of 0. So the N termini is going to be +1. The C termini will be 0. Now what we want to do is move in and look at each one of the individual amino acid R groups. I'm going to draw an arrow to the glycine. Glycine is a non-polar amino acid, so I'm going to write NP by that. That can't, regardless of the pH, the NP or non-polar groups, it's not going to change its protonation state. Phenylalanine, again, that's a non-polar, or that's an aromatic amino acid. That is not going to adopt a positive or a negative charge for that matter. The third amino acid R group is our aspartic acid. Now that's an ionizable group, but this is a polar negative amino acid. And the way that we've got it shown here is it is completely neutral right now. So it's neutral and it is protonated. Then if I had to guess, aspartate might be one of the places that there's a hang up, or asparagine. We're getting there. Threonine, this hydroxyl group, that's not going to be protonated any further, so that's not going to be ionizable, and it's not going to be able to take on the proton. Our alanine right here, that's a nonpolar group. Last but not least is asparagine. Asparagine is tempting. It is polar, but much like, and again, I have lots of young children, so I like to keep things at least PG rated. Unless we're talking about stinky socks, which that is, we get Pu. It's a polar uncharged amino acid. Okay, sorry for the distraction with the stinky socks. But ultimately, my point is that this entire polypeptide can have an extreme charge of +1. Now, if we go in the opposite direction, if we go from +1 and we deprotonate a group, well, the first group that we would deprotonate is this C termini, and that would get us to a molecule that has an overall charge. The next group that we could deprotonate, well, that would actually be the aspartate. So I'm going to change to a black pen. So this is a little bit more easily tracked. This is the first group. And if you're thinking, how do you know? Well, the way that I know is I know these pKa values well enough. If you had a table of pKa values, you would say, okay, well, I'm going to look at the lowest pKa value. The lowest pKa value of all of these groups are on the C termini. The next lowest is going to be the R group for aspartate, and the next group is going to be the N termini for the glycine. So we have a molecule that goes from a charge of +1 to 0 to -1. And let's see. Then when that is completely deprotonated, we're going to get to -2. So one of the things that I want you to be able to see with this, and that's important to see with this, is we have 3 ionizable groups. Therefore, we should have 1, 2, 3 pKa values. I don't have them. I mean, it would be like 2.1, 3.5, and 9.2. Those would be the rough numbers. They vary a little bit. But if you think about looking at all of these individual amino acids, what do we not have to worry about? We don't have to worry about the N and C termini of like every single amino acid. We only worry about the C termini of asparagine and the N termini of glycine. For anyone who was perplexed by this previously, does it make a little bit more sense? If so, add a slash to the chat. Okay. So this does definitely take time, and this does definitely take some practice to kind of analyze this. And I think, we jumped right here into an amino acid that has, could you explain the 3, 2, 1 in black again, please? So the 3, 2, and 1, what I was trying to illustrate there was to show if this molecule is completely protonated, what is the sequence in which groups get deprotonated? The first group is going to be the lowest pKa, which is approximately the 2.1. I think that might be where there's a hang up. Where did that come from? Well, that came from my head. And that's not where it always will come from. This would instead come from a reference document in your exam that has the designated pKa values. The 3.5 pKa value corresponds to roughly the pKa of an aspartic acid. The 9.2 corresponds to the N termini of glycine. So here what we're doing is we're looking at a polypeptide, analyzing all the possible charges. We could calculate, can the OH and threonine get deprotonated. Nope. Um, so, and one thing that is worth recognizing is you guys will have the pKa values. I will give you the pKa values on your exam, and those will be based on, you'll see a table that's like single letter code. What are the pKa values for the different groups on that? So you'd have to critically look at this and be like, do I use all of them for this amino acid? Oh, no, I don't. Okay. Or, oh, yes, I do. Okay. So a peptide bond, as I mentioned a little bit ago, isn't going to have a charge, in large part because it's resonance stabilized. It will not have a positive or a negative charge regardless of the pH. A peptide bond is going to display about 60% double bond character due to this resonance stabilization. So what that means is it's very rigid and it's very inflexible. Now, when you hear about proteins, and I know that I've used this term before, I talk about protein folding. So folding kind of implies, well, movement, not necessarily rigidity and inflexibility. Instead, okay, something that can move. Proteins move, but they don't move because of their peptide bonds. They instead move and fold in spite of their peptide bonds. Now, the angles that are adjacent to the peptide bond. So if we look at this shot at the bottom, here's the peptide bond. The angles adjacent to them and the bonds adjacent to them are going to have some sort of rotation. So what we have is, if you look at the, this is a little bit tricky to see. It's kind of a light blue. It's a little background here. That light blue background shows all of the atoms adjacent to that peptide bond. And think about them as being basically on one plane together. Are there certain amino acids that can do the folding or all? Every amino acid is going to be contributing. There are some amino acids that are a little bit more inflexible and some that are a little bit too flexible. And we'll get into those in just a little bit. Jada, that's a great question. I really like that. And just so everyone else who has asked questions, I like you guys' questions also. I just didn't say it there. Okay. So if you imagine, I always like to think about my palm as being the atoms or the flat plane that all the atoms that are near the peptide bond are. And then my wrist is the angle or the bond next to the peptide bond. So I can move my hand. Can you explain one more time how you'd be able to tell when they're allowed to rotate? I haven't yet gotten there. We will get there. So we've got a peptide bond that is this plane. Notice my palm is not shifting. So what that means, it's moving, but it's moving because of the bond next to the peptide bond. Okay. So we're going to get into the individual amino acids in just a little while because that's going to be useful for secondary structures. Now, the bonds, I'm going to go ahead and draw a little bit of a structure here. Remember, we got N, C, C, N, C, C. This is two amino acids, or the backbones of two amino acids. I'm going to put an X over my peptide bond. That C and N will not rotate. I'm going to put R sub 1 and R sub 2. This R sub 1 can rotate. And if it rotates, I'm going to draw it up here, R sub 1. That rotated approximately 180 degrees. It rotated despite the fact that this peptide bond does not move. This R sub 2 can do the same thing, that same sort of rotation. Now, this figure right here shows, or the figure below that structure, shows what bond angles are favorable. Now, the N to C, so from here to here, actually, I'm going to go ahead and put a little star over this. This bond to the right of the peptide bond is represented by phi or phi. There we go. So what that means is that this R sub 2 group, it can rotate. It can rotate either positive 180 degrees or negative 180 degrees. Now, the other angle to the left of our peptide bond, this is represented by psi. That's the psi angle, and that can also rotate positive 180 or negative 180 degrees. Now, with that, I want you to think about and look at these, like the contents of this graph. What this shows is these areas that are highlighted in blue or shaded in blue are where you can find favorable pairs of bond angles. So I said the phi angle, this R sub 2, can rotate up to 180 degrees. So that means it's up here. Okay. Well, in order to do that, you can look over here. The x-axis shows our phi angles. Okay. Notice how almost everything there is white. That's indicating that it's not a favorable or it's an energetically tough place to get to. So when you look at this plot, which is known as a Ramachandran plot, this shows the favorable pairs of phi and psi angles. So if I were to say, okay, what's a pair of phi angles that are favorable? Really, negative 90 for the phi angle, and let's say positive 90 for the psi angle. And if you're thinking, what's negative, what's positive? Well, this is our starting position. That would be, this would be 90, positive 180. This is negative 90, and that's pretty much where my flexibility kicks in and doesn't work anymore. If I rotate it any further, well, that's energetically unfavorable for Joel. Okay. So we have these combinations where it's like, okay, well, I can do this rotation, but I can't do this rotation. So when you have this peptide bond, well, this is favorable, but as soon as the other bond rotates in the opposite direction, that's too much strain. Now, what I want you to take away from this is that, yes, the peptide bond is the bond that remains stationary. Everything folds and rotates around that. That's what I'm looking for you to take away from this. In addition to that, I want you to know that the shaded regions of the Ramachandran plot show the favorable angle combinations. This is kind of like a, well, yeah, so I want you to look at that Ramachandran plot and say, okay, well, I see the favorable pairs. Now, next up is to talk about one of our important secondary structures. Our important secondary structures, of the two that are the biggest ones, you've got an alpha helix and a beta sheet. This right here is an alpha helix. This is stabilized by backbone hydrogen bonds. Primary structure is stabilized by covalent bonds, the peptide bond, which is an example of a covalent bond. This is our alpha helix, which is stabilized by hydrogen bonds within the backbone. Now, this is cylindrically shaped, and the height of one rotation. The way that I want you to kind of think about your alpha helix is to think about, okay, one rotation. And if you're curious, well, how I'm struggling to visualize that. I have two things that you might have near yourself. I've got a USB cable, because if there's one thing I have a lot of, it's USB cables, but rarely is it the one that I actually need at any given point. I also have a Diet Dr. Pepper can. What I'm going to do, and I want you guys to be able to visualize and try to do this yourself, is to take this one end of the USB cable and wrap it around this Diet Dr. Pepper can. and be able to identify like, okay, well, this is one complete rotation. So what I'm getting at is this length right here, the number of amino acids that would get from here to here, so to complete one rotation, is about 3.6 amino acids. Now, the height from where my thumb is to, I hope my fingers look like fingers. That's my index finger. So from my thumb to my index finger, that's approximately 5.4 angstroms. And if you're thinking, oh, angstroms, that is the family of, or that now I was just going to make a joke about it's a Swedish name. It is. It's going to Skarsgård, the guy who was in It. But there we go. It didn't work. So that's 5.4 angstroms tall. So I'm going to put this on here, 5.4. Not only does it have an awesome identifier, so it's not like millimeters or anything, but if you've ever seen the symbol for angstrom, I mean, look at that. That's just awesome to me. Now, each amino acid has approximately or occupies approximately 1.5 angstroms. Now, here's the difficult part about that. When we're talking about this being 1.5 angstroms, well, we're accounting for this in multiple different dimensions because this is 3D. What I want you guys to take away from this is the 3.6 and the 5.4. That to me is like the important numbers to walk away from this with. Now, from where my thumb is now to where my index finger is. There we go. Thumb to index finger. That would be 2 complete rotations. How many amino acids would be required for that? Well, close to or more than 7, but maybe a little bit less than 8. If I were asking for an average or a rough number, about 7.2. Now, the height of this is approximately 10.8 angstroms. Okay, could everyone give me a L in the chat if that makes sense, or a number if, wait a minute. Okay. Now, I think that getting something to visual, like getting a cylinder and getting a cord or something like that, or if you have a very large collection of sewing threads near your desk like I do, maybe you could get access to those. Okay, so we're building an alpha helix. We're trying to visualize that. About 3.6 amino acids constitute one complete rotation, and that one rotation is about 5.4 angstroms tall. This is one place where people have a tendency to get mixed up. An average alpha helix has about 10 amino acids. Okay, so we can take away from this some information. Well, if there's about 10 amino acids, then we're talking about, let's see, 7.2 amino acids is going to get us 2 rotations. So 10 amino acids are nearly 3 rotations. Hydrogen bonds are going to be parallel to the helical axis. So what's meant by that is in this rotation right here, my hydrogen bonds are going to be from my middle finger to my other middle finger. Now, the groups that are making these hydrogen bonds are going to be the backbone N termini and C termini, as is shown here. Here is a carbonyl carbon and an N termini. Anna asks, why are the rotations measured in amino acids, but height is measured in angstroms? It's a great question. And the rotations can be measured in angstroms. It just has to do with the 1.5 angstrom number. I just choose to use the 3.6 and the 5.4 because we're going to see some questions that relate to that, and it's very effective for problem solving. So the carbonyl oxygen is hydrogen bonded to the NH of the 4th amino acid away. So when you kind of count these out, you see a pattern. Okay, well, this amino acid right here, where I'm drawing an X, is amino acid number one. And then we've got two, three, four. Aha, that's where my hydrogen bond is. And I hope in just a second your question, my response will make a little bit more sense. Now I'm going to share this right here, but I'm also going to use this as a question, a poll question. So when you're ready, go ahead and think about this one and try to come up with an answer. In this one, you might get a little bit perplexed and say, wait a minute, is there a best answer? That's what I'm asking you to look for. Now, I'm going to walk through this one with you. How many amino acids are required for an alpha helix to span approximately 40 angstrom lipid bilayer? Okay, so what that means is we've got a lipid bilayer, and that is about 40 angstroms. Now, the first thing that I think about is I say, okay, well, 40, I'm looking at approximately 8 rotations, 40 divided by 5.4. And I'm doing rough numbers here. So 40 divided by 5.4 is about 8. I think it closed out the question to look at what you're doing, and I can't pull it back up. Anyone know how? There should be a button that has a little circle and 3 dots that says more. Click that. That should bring you to polls, and that should be able to help you out. So I'm thinking that this has approximately 8 rotations. Multiply that by about 3.6. 3 times 24, or 3 times 8 is 24 times 0.6. We're looking at about, what is that? We're looking at roughly 30. 26.6. So roughly 30. This is a question that I will give you more precise answers rather than these rounded answers on the exam and stuff. But does everyone understand how to do this? Can you explain your logic yet? Absolutely. So what I've got at the top is my lipid bilayer. I've got my lipid bilayer, and I've got an alpha helix. I'm going to switch colors to show this alpha helix. And this alpha helix needs to go from here to here. Basically, it's almost like it's an earthworm that needs to be present on both sides of this lipid bilayer. Now, this is an alpha helix, as we see in the problem. The question is, well, how many rotations are needed for this? Well, then the question is, okay, well, each rotation, one rotation, is 5.4 angstroms. One rotation is about 5.4. I'm going to put that at approximately 8 rotations. Each rotation is about 3.6. Sammy asked, could we divide by 40 by 1.5 as well? I believe that would work out just as well. So that 8 times 3.6 gets me to 2.6 or 26.67. Ernest asks, what's the 3.6? The 3.6 is there are approximately 3.6 amino acids per rotation. My logic was I wanted to find out how many rotations there were to cover 40 angstroms. That's where the 8 came from. Each one rotation is 5.4 angstroms. So I did 40 divided by 5.4. I came up with a rough number of 8. So roughly 8 rotations. These 8 rotations they each have 3.6 amino acids that make them up. That's where that came from. I got a private message. If we chose 25 because we did the exact math, is that okay since 26.66 is closer to 25 than 30? Yes. Okay. So that's one sort of question that I want you to be able to solve there. I'm going to go ahead and end this poll. And let's see, going back. Okay. Now we've got, yeah, we're doing fine. The next question is how tall or long is the alpha helix with 110 amino acids? So this is another sort of problem where you could say, okay, well, I'm going to do the 1.5, 110 amino acids, 1.5 angstroms per amino acid. So 110 times 1.5, and we get, calculator, approximately 165. Wait, no, that's wrong. Joel, 110 divided by, yeah, that's just a second. 1.5. Yeah, no. 1.5 times 110, 165 angstroms tall. Alternatively, you could say, okay, 110. You could figure out, well, how many rotations are there? 110 divided by 3.6. And then we get, that would be 30.5. Take that 30.5, multiply it by 5.4, and you get 165 angstroms. Okay. Um, and then this is another angle that you could look at it, but I actually solved this question this way by doing this right here. The question on the next slide reads, how many rotations are there in an alpha helix made up of 110 amino acids? Well, you say 110 divided by 3.6. And that's where you get the 30.5. There are 30.5. Okay. So these are all just the different ways in which we can see this sort of problem. Um, Now, with that, I'm going to go ahead and move ahead to a beta sheet. We're going to come back to that helical wheel on Wednesday. Um, but I wanted to get into this so that we can cover the two big secondary structures. Your beta sheet is the other major secondary structure. Now, what makes a beta sheet a little bit different from an alpha helix is that it's a little bit more of a larger thing. So when we looked at an alpha helix, it was easier to pick out like, oh, okay, there's the R group and there's the N termini, there's the C termini and everything like that. When you look at a beta sheet like this depiction right here is basically these parts. So it's tougher to see that molecular snapshot. Now, one of the things that I want you to notice, and I'm going to throw this up as a poll question, I want you to look at these two different um, beta sheets, and I want you to answer which one you think is a little bit stronger and go from there. So we've got our beta sheets. It's stabilized by hydrogen bonding between the N termini and C termini. So here's a hydrogen bond, here's a hydrogen bond. There's so many different hydrogen bonds there that stabilize this. Now, I've given you a couple of different answers. We've got anti-parallel, parallel, invulsive, and transcendiary. One person has decided transcendiary. Bold move. It's not transcendiary, but thank you very much for throwing that answer option out there. Which, if you're ever taking an exam from me and you see a word and you're like, I've never seen that word before in my life, I probably made that term up. So don't fall for that. Um, so parallel or anti-parallel is really what it's all down to. The popular answer right now is anti-parallel. And in this case, the popularity contest does emerge and does win. The reason is because these two hydrogen bond donors and acceptors are directly across from one another. Whereas in a parallel beta sheet, you've got the two groups that are kind of staggered with respect to one another. Now, I'm going to go ahead and end the poll there. And I'm going to We've got some closer questions, but that's not right now. So your beta sheets are going to be stabilized by these parallel and anti-parallel depictions, or options, basically. Now, when you look at a beta sheet and you look down here in the lower left-hand corner, you've got tons of different models for them. I would think the R groups would repel one another in the anti-parallel conformation. One of your classmates has a very good perspective and a very good thought there, because what I said earlier was R groups don't drive the formation of secondary structure, but they can disrupt it. Now, we're going to get to that in just a second, but in the meantime, what I want to show you is what does a parallel versus an anti-parallel beta sheet look like? Parallel versus anti-parallel has to do with the directionality of that region of a peptide. So I'm going to draw a little line here. This is the N termini, and here is the C termini. Okay. Now I'm going to switch colors. This right here, this region, would everyone grant me that I've drawn an N and I've drawn a black line slicing or pointing out the N of that peptide, and now I'm drawing a line depicting the C. Okay, will everyone go with me that this is showing the directionality of this region of this peptide, N to C? Okay, got a yes. Now, what I want to do is I want to show you that, well, if we continue following that peptide and we catch the second half of that little loop, we've got the N termini right here and the C termini right there. Could you give me a 1 in the chat if you follow both of those N and C termini designations? Okay. Now, what I'm showing you there is that this is all the exact same peptide, but these two do not line up. The N termini and C termini do not line up. Meanwhile, I'm going to draw another one where I show that the N and C termini do line up. Okay, so here's my peptide bond. So now I'm going to change colors just so I can clarify this. This is a relatively N terminal. This is a relatively C terminal. This is the N, and this is the C. So when we look at our N termini and C termini, the terminal ends here, are they going in the same direction or are they going in opposite direction? If they are going in the same direction, like what we have here, where I've drawn a star, they are parallel. So this is parallel. Think about them as being like your two cars going in the same direction on the highway. Whereas over here, we've got our anti-parallel. Are the N termini and C termini of these peptides pointed in the same direction? If the answer is yes, they are, that's parallel, that's weaker. Oh, man. Now, I'm going to kick the closer questions up because I wanted to get through parallel and anti-parallel, and I feel all right about that. You guys are welcome to answer those questions, and then have a great day. We'll pick up the rest of this stuff on Wednesday. Wednesday, not Thursday. If you have any questions between now and Thursday, please don't hesitate to drop me an email. I've got office hours on Wednesday at 12:30. If there's another time that works for you for office hours, email me and say, hey, can we meet at this time for office hours? I've got some questions. I'm glad to do that. Okay. In the meantime, have a great Monday. Have a great Tuesday. I'll see you back on Wednesday. And thank you very much for coming to class. I really appreciate it. Can we go over this slide again next? Yeah, absolutely. I'm not sure if I logged into the Zoom how I should have. It didn't give me the prompt. Can you check if I'm getting credit somehow? You should be, because I can. What I'm always looking for is first and last name capitalized. That's my indication that you did log into the SSO. It's whenever I see like George's iPhone logged in that I'm like, oh, that's not the SSO. A peptide makes an alpha helix, and that alpha helix has three complete rotations. Approximately how many amino acids were required for those rotations? That question I did not go over. There's about 3.6 for each one of them, so roughly 10. Romy, I presume that you were sending that to a friend and saying, "Dude, this guy asks the best questions."
Bye, thank you. See ya.
Absolutely.